Firstly, I repeat that next time we have the test and the contest, and you and your teammates is warned about that. Okay? Okay. So, today's topic is Cartesian tree, and it will be, of course, very short. So, we, uh, I think we finish in 1 hour. So, you will be very early today, and if you have questions about second model, you can ask after the this lecture. So, yeah, today. Today's topic is Cartesian tree. So, firstly, what is the definition of this data structure? What it means when we say that we work with the Cartesian tree? Do you know what is the difference between trees that you work with in other courses and this? No. Okay. You know that binary tree is a tree where we can place nodes in this order, and you know that if we work with the binary search tree, that we have one property. What is the property of binary search tree? You know? Yeah, yeah, yeah. It's about uh, mm, we yeah we write it like L or R and T, and we know that there are three numbers here, and L is minor or equal than T, K, yeah, and T, K, or equal than R. Yes? So it's the first property of the Cartesian tree. Usually you can find the shortly abbreviation of the Cartesian tree equal to trip, because it is trip property plus heap property. So, firstly, of course, we think that there is tree property that left subtree contains nodes with the k with that is smaller than k of the root, and that there are keys with the keys with there are nodes with the keys bigger than key of the node. Okay, it's about tree property and about heap property. You know that heap, if we work with the heap, there are one property of the heap. What is that? For example, maximal property. That root has the maximal number in it. Yeah. So of course, if we try to make a heap property from this picture with the keys, we make a contradiction because if t is the maximum or tk is maximal, so right subtree is empty, and it is a very bad tree, I think, because it will be linear to the left. So, of course, we want to make a heap with the other points, with the other numbers, different from keys. So we say that every node has a priority number. I shortly write it like Pn. And so T and P will be bigger than L and P and bigger than R. And of course, this property will be true for all of the nodes in this tree. Yeah. So for all nodes in this tree, we say that key is bigger than left key or less than right key, and priority number, P and here's NP, think it's Pn2. Yeah, and so if our structure has these two properties, we say that it is Cartesian tree. Okay, I write it. Okay. And usually we say that Cartesian tree, it is binary search tree by the keys, and it is heap by the priority numbers. Okay. So let's try to make an example. Firstly, Firstly, I write here keys. And can you say some numbers, some integer numbers? In different order.
7, 6, 8, 2, 8, 1.
It can be bigger than a 10.
Yeah, yeah. Checking.
Okay. Then to make a Cartesian tree, I reduce it. Окей. Это видно на видеокамере? Okay. So, to make a Cartesian tree, firstly we find the maximum priority key, because we know that the root of this tree it is the maximum, it is a node with the maximum priority number, yeah? So it says that this node will be the root of the Cartesian tree. And I write here yeah, it is the root of the of this tree. Okay. Then when we set the root of the binary tree, we can split our numbers into sets with the keys less than 9 than in the root, and with the keys bigger than 9. And it is left subtree and it is right subtree. So then we recursively repeat the step of the algorithm. I find the bigger priority number here, and I see that there is only one node, so I write it here. Yeah, it is 10, 12. It is the maximum priority key. And here is the maximal priority key. I write here as too. Then I repeat for this part. I find maximum. It is 9. Yeah. Four, 9. Then it splits into two subtrees. I find maximum in each subtree. It is 7 and 8. Yeah, so I write here to 7, and here 6, 8. And then Yeah, I see that there is two children of each node here. So I write here 1, 5, 3, 6. And here 5, 2, 7, 1. Okay. And we have a Cartesian tree. Yeah. So firstly, we can compare the height of this tree. It is equal to 4 or 5, yeah. And we see that it is nearly to this number. So it is not unique that if we make random priorities that we get a tree with the asymptotical height equal to logarithm from the number of nodes, because it is true that of course, I don't know. Do you have probability theory as the other course in your program?
Now we will later. Next year, I think.
Next year, not now. Okay.
So,
So I write here one statement with the thing from the probability series, but we don't prove it, and you can understand it as a average. You, I write expected value. Do you know what is the expected value of the variable? Not. Okay. So I write it here that if make trip with random priority number. The expected value of the height tree is asymptotically what it means? It means that if I make a permutation of these numbers and write down all the trees that I can make with the priority numbers with these keys. So I find that in most cases we get the tree with a similar length, with similar deeps of it. So it means that if initially we have only keys, so and we want to make a tree with the short depth that will be nearly equal to logarithm asymptotically, of course. So we can make it with random parity numbers. So this way is very good way to make a very compacted tree. Because if you make, for example, a binary search tree by induction algorithm, you can, for example, get a very linear structure with the asymptotically n depth. So it is about advantage of usage of this structure. Firstly, because of very very small depth of it, and of course a second advantage, it is the two properties that we get of it. Okay, so it's about and tasks where we use Cartesian tree you get in the new contest today. And now we talk about operations. There are two main operations that you can use to implement others, and it is split and merge. And the others are built using this operations. So, do you know what means split the tree? We make two trees, we split it, for example, by key. Yeah, we have, for example, key for example 6, and we want to make two subtrees. Yeah. So of course, if we take a look at this tree, we see that there is place where 6 in it. And for example, if we try to divide it here, we see that all the numbers that is smaller than 6 in the left subtree. So we add these nodes in right subtree and try to split it here. Then we see that this number is bigger than 6. We repeat this algorithm, and we see, for example, here that we have new that we have number that smaller than 6, and we with the parent with a number bigger than 6. It means that we need to split it in this way, of course, and we repeat it recursively, and when we split the subtree, we can change the child of this node. for example. Yes, because we make two subtrees. We know that this is the left subtree of the left part of the splitting. Yeah. So if we get the split of this tree, of course, if we split this tree, we get such subtrees, yeah. This is splitting this tree. Then we can connect this node with the new, with the left subtree here. Do you understand me? No? Okay. We know if we have 3 nodes, if we find 6 here, it means that this node will be in the left part and these two in the right part. Yeah.
6 is included in why
Hmm?
6 is included in why we are not including in the sub.
In the left? Oh, you mean, yeah. Okay, yeah, you're right. It's not so. Yeah, it's not so important, but okay, we can connect like this. Oh, no. Yeah. Like this, yeah. Okay. Okay, and then if we start with the recursive algorithm, yeah, then we can race with these two subtrees, yeah, because when we go up in this tree, you see that this number is bigger and it connects with this number. It is the root of the right subtree. Then we go up and and we see that there are 2 trees that make by splitting. Okay, so if we make an algorithm, yeah. If we have this tree, this strip, and we have a key, I name it as the splitting key. Yeah, initially we have this number and the trip. So firstly we compare tk with the sk. So if sk is bigger than tk, it means that we need to split right subtree. Yes. And in this case, in this way, if sk bigger than tk, if we split right subtree, we get two new trees. Yeah. We name it like A and B. With the numbers that is less than sk and that is bigger than sk. Okay, and then answer here it is these two trees. Okay. And if sk less or equal to tk, very similar. Yeah. So we divide into parts left subtree. And then we write the answer like t with the like a, yeah, it's number that less than sk, and t with two subtrees b. And right subtree. Okay, it's about splitting. Is it understandable? Yeah. Then second operation, it is merge. And firstly we have to trip. It is L and R. And we merge not any trips. Here we make one restraint to these two trips. We say that initially all the priority numbers in one trip will be less than in the other trip. Or all. Yeah. it's important to working of the algorithm of merging. That we can merge only two trees with the I write again NP and Peretz number. Yeah. It means that Peretz number in one tree will be bigger than in the other. Okay, and we have this tree after splitting, and we see that in this we see that if we merge these two trees, we make this tree again. I try to maybe compare it. There is no way to copy it. I think it's right here, this clone. Yeah. Okay. So, okay, I compare these numbers. No. No way. Okay. Remake. Do you write these numbers in your notebook? Okay. So, we have nine?
Six, nine.
Oh,
It's nine. No, no.
oh, okay. Yeah. Yeah. Hmm? Okay. And after splitting, we split it by 6. We get two trees. And I name it like L and R. Yeah, in R we have 9, 13. Then 10, 12. Okay, and Peretz numbers. Yeah, you're right. Okay, then we need to change it. Yeah. Okay. And if we have 14, yeah, we have only right subtree here. Then splits into 2. Yeah, 8 and 11. And 10 and 12. and left. For 9 is the root. Then here is 6, 8, and 5, 2. In this way to 7 and with 2 children. 5 and 3, 6. Okay. Is it understandable how to build it? Yeah. Then, how to merge these two trees? In this example, it will be in one step, of course, but then I write here the common way. Initially, we say that the maximal Earth numbers is the number in one of these nodes, because it is bigger than other parity numbers in this tree, and this number is bigger than other numbers here. So the root of the finish tree is one of these nodes, and we see that it there will be this node. Yeah. So I write here 7, 14, and then we know that the all of these numbers is with the private numbers. Okay. I think. No. We need to case, yeah. And here too. And so in this case, we can replace it with the right trip. Okay, 8, 11, and 7, 1. Okay. In this way, we see that the bigger number 9 and 13. Yep. Okay, and we see that this number will be less than this number. So I can recursively merge this tree with this subtree, and I can write this subtree as a subtree of the new tree. So I write here 10, 12. It is the right subtree of new. And then I compare this node with this node. I see that 8, 11 is smaller. yeah, 11 is smaller than 9, so I write here 8, 11. Then I merge this trip with this subtree again. And then I see that the last number is 49. Yeah. In this case, I see that I need to merge this tree and this subtree, and it will be the subtree as the left subtree of the new trip. Six. And if we compare these numbers, we see that 6, 8 is bigger with the bigger pairs number. And as this number is bigger than 6, I write it here. Due to emptiness of the right subtree. And 5, 2 will be is it equal to the first trip? Yeah? Okay. So we see that merge will be the inverse operation than splitting. Okay. So in the common way, firstly, we compare it will be RT will LT. Compare RT K and RT K. And if TK is oh no, we compare priority numbers here. Firstly, we compare priority numbers. These two priority numbers. Yeah. And if a right priority number is bigger or equal to left priority number, so in this case, it means that RT will be the root of the new trip. And I name it as RL, RR, L, L and L. And in this case, we know that all the numbers in left subtree will be less than this, so we merge left subtree with L and RL. Yeah. And here we don't touch right subtree. Yeah, and recursively repeats these steps. If smaller than L. In this case, the root of new tree will be LT, and here will be, and there the answer of merging L, R, and R. Okay? So now we know two operations, merging and splitting, and to implement other operations, for example, insertion, we use these two operations. For example, we have new number, for example, n, and t as a trip. So to firstly, what we can make? We can split this trip into subtrees. Here will be number x such that xk smaller than n. Here x such that bigger or equal n. Yeah. We know how to split trip by the number. Then we know what is the maximum number priority in the trip. Yeah. I write here it like example y maximum priority number in C. It is a priority number of the roots of this trip. Yeah. So then we make new trip. Here n. And here to L. CR. Yeah. Do believe that it is right trip after inserting n. Because firstly, we know that the keys in the left subtree is smaller than n, and in the right bigger than n. And the priority number of new nodes is bigger than all priority numbers in these two subtrees. So two properties of the trip will be true in this case. So it is trip. Of course, it works due to this possibility of our algorithm, because Peretz number usually it is number that we made in the trip. So it's about insertion. If we want erase the number, how to erase number? Firstly, we can split by this number. Yeah, we have n and t. So firstly, we can split t again into subtrees. And for example, we find n here. Then we know that there is two cases. N will be the root of this strip, and for example, n will not be the root. If it is not the root, we repeat this algorithm. Repeat while n is not root. So I can think that n is the root of TL, and then I know that TL it is n and two subtrees A, B. And we see that if we erase n, we get three trips A, B, and TR. So next step is to merge A, B, and TR. You see that the keys in these trees trips will be in A will be smaller or less or equal to B, in B will be small or less or equal to TR. So we can merge it. Of course, we merge, for example, initially these two and then these two. New trip and TR. Of course, if n is not the root of the TL, we recursively split it in two trips and then recursively merge it. So, what is the time complexities of these algorithms? For example, insertion.
I think first we have to know split and merge.
We use splitting here, and we use we don't use merging. We use only splitting. Okay, and what is the asymptotical time of splitting? Oh.
tree? No.
Hmm?
The depth of the tree?
Mm. We compare their roots and then we go down in this tree. So I think that it's the sum of the depth of these two trees. Time complexity. It is O from depths of uh, oh no, oh, depths only one depth. Yeah, yeah, yeah. Was a tree. Because we go down here. Number of times is equal to depth of this. Yeah. Okay, and about merging, if we merge these two, we know that it will be equal to depth of this new tree, and it is asymptotically the sum of these trees. So here is time complexity equal to
Depth of LT?
yeah.
Or F? Depth of L. What's the
I write here L plus R as the number of depths in this strip and this strip. So if we insert number, we use only splitting. So time complexity O from depths. O from T. And here it is interesting that number of merging will be asymptotically equal to depth of T. For example, if we have such trip, if we try to split, then we repeat it with the n. It will be. But I think time complexity will be 2 equal to O from depths. Because new subtrips will be because if we merge very similar subtrees, it will be quicker, and I think we can speed up it to linear time. But if we look at this, algorithm, Of course, it is t in power 2 because we spent from depth of the number of operations of merging, and all merges will be the time of merging will be equal to O from T2. Hmm?
We will split recursively and then merge.
Yeah, we recursively merging, so we spend squared time because we um,
Yeah, I think
we execute merging O from T numbers, and it spends O from T numbers too. So asymptotically it will be in power 2, but I think it's the upper bounds that is very unexpected. So usually it will be near linear time too. So it's about two operations. Of course, there are other operations of Cartesian tree, but all of them is based on merging and splitting, you see. So when you implement this class, you firstly write splitting and merging, and then implement other operations using it. I think that it is all that I want to talk today. And can you yeah, I repeat that next time we have theoretical test and contest. In contest will contain dynamic programming, DFA, and this topic too, Cartesian tree. So, and test.
yeah, see, that's really
Mhm.
same.
Yeah, the same. So that's all. Thank you.